So we shorted out R2, and then that was gonna, so that would end up, so then we had to see what would be the effect of it. So on this one here, let's just do it we're going to do it the long way and recalculate out what our new voltages would be so that we can see what's going on with our voltages. Now yesterday when I was doing it, I kind of was doing the speed brush. And if I have my shorted R2 and I got my red lead on, well, if I have it on A and I got my black lead on my reference, I know that I'm measuring across my short, but I also know that I'm measuring across my power supply. So I know that I didn't change anything to do with my power supply, and so that I know that test point A is always going to stay at my source voltage. To get down to B, now I get on the other side of that resistor there, that one series resistor here. That kind of throws a lot of stuff in the mix there. So once that R2 got shorted out, that voltage across from, let's see, what would be an easy way of doing it. So that voltage from here to here, since I shorted that out, this parallel circuit here ended up decreasing in resistance from here to here. So once that voltage from here to here ended up decreasing in resistance, I know that that voltage drop across C is going to drop. And then since the only difference between C and B is that switch makes B to be in the same value, so I know that B drop, A is going to stay the same. So at this point here, we knew that those are all going to drop because that resistance of this whole circuit ended up dropping in resistance. So if this voltage here dropped, then I have a voltage divider formula across here. And so now I'm taking a new, even though this value of this series circuit of R3, 4, and R7 is going to divide up that new voltage that dropped, and that's going to divide up differently. So then I know that E is also going to drop because my source voltage has dropped. And that's just based off of my voltage divider formula. But then we got down to here, and then this is where it got kind of messy here because it wasn't obvious what happened to test point D, whether if that one increased or decreased in resistance. Well, the general rule is if I'm not measuring across I'm not dropping across my source, or I'm not measuring across my short anymore, and just from just kind of the troubleshooting, I knew that once I got on the other side of that short, I knew that my test point D had to go off. But it was hard to see it because we already said that this dropped, so then we would assume that this would possibly drop. So let's take a look and see what actually happens when that drops. Because even though that test point C dropped in voltage, R2 is no longer in there. So it gave all the other voltage to R5 and 6. So that's going to end up going up. And you can always double check your work because if you notice that you're not measuring across your short anymore, that those voltages are probably going to go up. So let's see what would be the easiest way. So if we assume that, so let's just take it the long way. So we know that R2 is shorted out. So that changes our circuit. We know that R3, 4, and 7, that one didn't change at all, so that resistance is okay. We don't have to recalculate out that one. Now R2 is no longer in the picture, so the value of R2, 5, and 6 is going to equal to what now? If I add those, if I'm just looking at the series circuit there, and if I add those two up together, I would end up with what for R2, 5, and 6, assuming that R2 is shorted. What would I get for resistance for that branch? That makes sense of what I'm asking for? Okay, so R2 is 0 ohms now, right? R5 and 6 is combination of those 88 ohms, what would I get if I add 0 ohms to 88 ohms? 88 ohms, okay? So now let's change to so now this one changed to 88 ohms. So we don't have to do anything more with this circuit because this is the only thing that's changed. This is the only part that's changed. So now we want to go over to here. So now, what do I get for the combination of R2 through 7 now? What would I get for the new resistance of that one? So now I'm combining these two that are in parallel. I'm going to take my 112.7 ohms and my 88 ohms, put those in parallel. What do I get for my new resistance for those two?
49.42 ohms.
Okay, say that one more time.
49.42 ohms.
Okay, so 49.24 ohms. 42?
Yeah, or is it 2.4?
Oh, did I say? Oh, yeah. Like I said, I had to exercise a little bit. Okay, so then, now we just got two resistors. So now what we want to do is we want to kind of work our way backwards. So first of all, we want to find out what is our new voltage drops across R1 and then R2 through 7. So using our voltage divider formula, let's just take our 24 volts and divide that up proportionally across these two resistors. And what would I get for voltage across R1 and then also through R2 through 7? Once you find the value of a 1, the other one is just the remainder of the 24 volts. So it doesn't matter which one you calculate off, and just take the remainder and the rest of it goes across the other resistor.
For R2 through 7, I got 19.96 volts.
18.96 volts, okay?
For R1, I got 4.039.
What was it?
4.039.
Okay, and if I add those two up, then I would get my my 24 volts. So then that still gives me a voltage at test point A of what for a new test point voltage.
24.
Yep. Plus 24 volts. Test point B is going to equal what?
19.96 volts positive. Plus.
Positive. Okay, and then test point C?
Same.
Same. It's just going through the switch. And then F is always going to be our plus and minus 0 volts. Okay, so there's our new voltages, so then we can kind of bring those back over to here. So now I got plus 24 volts, plus 19.96, plus 19.96. And F is still plus 24. So then we just so we're going to kind of bring our way back. So then we know that A is still going to be at plus 24 volts. B is going to be at our 19.96 volts. C is going to give us 19.96. And now, so the only one that we were really kind of questioning on was is test point D. So we have enough information now to really figure out what's that voltage across test point D. So what would be my voltage at test point D? So the way of looking at this is at test point C I have a positive 19.96 volts. And if I go through a short, that's basically like me just connecting test point C to D together, right? So what would I get at test point D?
19.96.
I get a positive 19.96 volts. So then if I compare it to what my original one was at positive 17.77 volts, now it's at a positive 19.96. So test point D indeed increase in voltage. So the minute I went on the other side of that short, test point D ended up going up. Now test point C, to verify it on this side, test point C, now this is at, test point C was 19.96. So that's the same. It used to be 20.19 volts going from here to ground. Or it's also the voltage that has to be divided up amongst these two. I can bring it over to here and take a look at it. And so I can see that that voltage across my test point C did indeed decrease. And since the resistance of any of these didn't change any, I'm taking less of a source voltage going into my parallel circuit, and I'm going to divide less of a voltage across these two resistors. So that means that voltage across both of these resistors ended up going down, and since R7 ended up going down, so did my test point E then also go down. Okay, so that one ended up going down, but test point D did indeed go up once R2 shorted out. Once I got on the other side of that, on that other side of that resistor. Let's see. I don't like to do this. It's kind of a neat little trick, but it can kind of throw you off. Let's see. So 19. That one. Put in test point. What would be the voltage at? We don't even. If we're looking at. Let's try it. So. Let's see here. So if I'm only looking at, let's just kind of look at it as this one path, and we have all our new test point voltages with R2 shorted out, and I'm just looking on the right-hand side of that path there, I know that test point A stayed the same, test point B ended up dropping, that was at a positive 19.96. So this one ended up dropping. Test point C ended up dropping. Test point D ended up increasing. And test point F ended up remaining the same. What you can kind of do is that if you watch the arrow, since test point A and F, those remain the same. I know nothing happened to my source voltage. Nothing happened there. So then I know that at that point then that something inside my circuit had to go wrong. And if I look at my arrows, you can see that as I look down through my circuit, this one went down, and then also this one went up. And you can see that the direction of these two arrows are actually facing to the problem of the trouble. So if you're really confused about what happened or where the problem went, and if you draw the arrows, and if you know that your test point A to F remain the same, you know that your source voltage is good. If your source voltage, something happened to your source voltage, either test point A would have probably did a change. So since test point A never changed and I'm referencing my ground, I know my source voltage is good. And then if I look at all what happens to my new test points, so if I don't even know what happened with my circuit, let's just say we didn't know that R2 went bad, and all of a sudden here's on the schematics they're telling me that these should be what the test point voltages should be. And all of a sudden I go and do the measurements, and all of a sudden I go to this one and I go, oh, that one went down, oh, this one went down, oh, this one went up, and then this one remained the same. I can go back and go, okay, where did my arrows change directions? Well, my arrows change directions and they start facing each other at this point. So then I know at that point that there's something wrong with R2. I still might not know what's wrong with R2, but I know that's where my problem is. Okay? So the problem is when I'm doing this, to me it looks obvious because I already know some of the tricks and techniques of doing this stuff. So it's pretty obvious to me, but all of a sudden, so like yesterday when I was trying to do the speed rush, and I knew exactly what was supposed to happen, but that was because I was kind of doing the arrow method. I already knew that as long as I'm measuring across the short, I know my voltage is going to go down. The minute I went on the other side of that, opposite side of that short, I knew that that voltage was going to go up. Just because it always happens. It's just kind of one of those routine things that you can do to double check your work. As I said, there's always ways to double check your work. So I know if I'm measuring across my short, my voltages are going to drop. The minute I get on the other side, I know those other resistors had to make up for those voltages, and I knew that that voltage had to increase. This is a whole other separate circuit, so I had to analyze this one a little bit different. And since nothing changed in here, I knew that my source voltage across the circuit had dropped, and so then I knew all these resistors ended up dropping. Okay? So sometimes, we just have to go back and recalculate it all out to see what's going on. Do you have a question there, Nick?
I was wondering, so that works with just shorts, right?
Nope, it works with opens too.
Opens.
The only difference is that the arrows go the other way.
All right.
Yep, the minute the arrows change directions, if they go, either they're pointing into each other or pointing out.
All right.
Yep. Yep, so it works either way.
Just different directions.
Yes. We can make up a simple series circuit and stuff, and I can show you that. But it's kind of a neat little method, but I actually have a whole bunch of rules about how to use the arrow method and stuff like that, but they kind of, problem using the arrow method, if we always just try following the arrow method, then we don't understand the concept of the circuit. And so I like to make sure that people understand the concept of the circuit and how to troubleshoot it, so we can understand how these circuits work. All right, any questions on shorted R2? Does that make more sense? Yeah, and once you get the hang of it, then you can you have a pretty good feel for it. And like I said, typically, right now I'm telling you what the problem is, but out in the industry, it's going to be just the total opposite. We're not going to know what's going to go bad. So we're going to go ahead and the first thing that you always do when you're troubleshooting is first, find out, do I have my source voltage? And is it the proper voltage? Just like when Bokai, Melissa, and Brad were in lab, they were doing their lab, what was it, lab 9. Lab 9, and they identified that when they took out their series resistor and went just with their parallel circuit, there wasn't enough current to power up that parallel circuit. And they knew that they should have gotten their 10 volts going across their parallel circuit, but they were only getting something less than 8 volts across it. And so they were trying to figure out what happened. Well, what happened was that when they removed this series resistor out of here and they went right to a parallel circuit, it was drawing too much current and their power supply was dropping. Their power supply was dropping from 10 volts down to less than 8 volts. It was like 7.4 volts or something like that. So if they were to troubleshoot something, first thing they would have done, they would have went to test point A to F to verify that they have their source voltage, and they would have identified that their power supply was losing its voltage. Now it could have been several different reasons. One was the circuit wired up right, or was it just that the power supply itself didn't have enough current to supply the circuit? And that's what their case was, is that once they went into that parallel circuit, it became so conductive that the power supply couldn't handle the current and stuff, and so their voltage dropped. So at that point, you could consider that maybe it was a faulty power supply, or we were just underrating our power supply. So at that point, that would have been the problem. So that would have been the first check. Okay, do I have my source voltage? Yep, I got my source voltage. That's all stayed the same. Then I go to test point B. Oh, that one dropped. So the minute I knew that, once I got on the other side of that resistor, the minute I knew that one dropped in voltage, I knew that I had to have a decrease in resistance. So I knew that one of my resistors probably decreased in resistance. It doesn't necessarily have to be a short, it could have just been a decrease in resistance. So at that point, we could identify, okay, yep, I got something wrong with one of my circuits. Now which one is it? So then I'd be going through, then I'd go, maybe I went around this one, and I knew this one dropped, and then I'm back to 0, and that stayed the same. So now I go, so I know that all these ones dropped. So it didn't really change anything. I didn't get any change in, this one dropped, and then this one stayed the same. So I knew that at this point on this side of the circuit, nothing changed. So now if there was no changes on this side of the circuit, I know this circuit probably is good. And then I come back over to this one, and all of a sudden I go, this one dropped, whoop, that one went up. So at that point then, I knew that I probably found that problem somewhere in between these two test points. The minute I seen that change, then I knew that I was on this side of the circuit, and then it was going to be in between those two test points of where that change was. All right, let's. If you don't have any other questions on that one, let's take a look at our next one here. Let's get rid of.
For R1, you said that you had a decrease in resistance?
R1 had no change.
Test point B.
The voltage across it increased. The voltage across R1 increased. They had to make up for the rest of the voltages on the other ones. Because the minute this one shorted out, it lost its voltage, right? So then it had to divide up all the other voltage across all the other resistors.
I see.
So to make up, because no matter what I do, even if that one shorted out, no matter which way I go, since I know that test point A remained the same, if I come down and I have all my voltages across all these, I still should equal 24 volts. If I come down across here, I know I still have to equal 24 volts, no matter which path I go.
I see.
So that means that since this one lost its voltage, these other ones had to make up for the difference.
Yeah, that makes sense.
Yeah. All right, what's our next one here? So that's shorted R2, so
Open R6.
all right, open R6. So this one we're going to just go ahead and remove. So we know that we have an open R6 that's no longer in our circuit, and we know that. And what do I measure across and open? My source voltage. My source voltage of my voltage that's going into my parallel circuit. But since I know that this resistance of this parallel circuit has changed, then I have to go back through and recalculate out everything for this particular parallel circuit. So we need to know what is that new source voltage. So what is the, so now we got, so what is my new value for R5 and 6 here? 120 ohms. nothing changed here, but R2 and 5 and 6 has changed now. So now R2 and 5 is going to change to what? How much resistance? So R2, 5, and 6, those are wired up in how? Either series or parallel?
Series.
Series. So how do I add resistance in series? So what do I get for my new value for R2, 5, and 6? 132 ohms. Okay, so now I got brace I'll use. So now R1 stays the same. Now what's my new value for R2 through 7? .79 ohms. Okay, and then if we use our voltage divider formula, what's our new voltage drop across those two resistors?
R1 is 3.39.
3.39.
Yep.
26 point.
Nope.
That's 20.61.
Oh, 21.
20.61.
20.61. There we go. Got it. All right. So what's my voltage at test point A at then?
24 volts.
Plus 24 volts. And then test point B
Plus 20.61 plus.
plus 21.
20.61.
20.61 meters. All right, and get this one right. I won't even ask you. Since you guys can't give me the right answer. All right, so there's our new voltages there. So we got plus 24 volts here, plus 20.61 volts here. Those. Okay, so now what's my, let's see, so we opened up R5 and 6, so what's my new voltage drops across R2 and R5 and 6? answers yet? So that's my new voltage across R2 and R5 and 6.
R5 and 6, 18.74
18.74
volts.
volts, all right? And really, though, we don't even need to calculate out R2 because we have enough information now to calculate out, because we're really only looking at our test points. We really don't even need to know what that voltage across R2 is, because we know now that test point D is going to be what voltage? What's going to be test point D now?
18.0.
Yeah, positive 18.74 volts. Then we can do the same thing with test point E. So just figure out what the voltage drop is across R7 now is.
860 millivolts.
860 millivolts. Okay, so now test point E then is going to be positive 860.0 millivolts. All right, and we have all our new test points, so we know that our new one here is 24.00 volts. Test point B is going to be 20 volts. All right, so there's our new test point voltages. We know that test point E to ground, we still have our positive 24 volts, so that one's remaining the same. Test point D did what? Increase or decrease?
Decrease.
Increase. So since we know that our voltage increased, we know that we probably have some open now.